Welcome to Center Math Problem of the Week. For this week's problem, we denote s of n as the sum of the digits of some integer n. And we want to find the smallest positive integer p such that s of p equals s of 2p equals all the way to s of 2014 p. So the first thing we can do is note that we can note 9,999 times k, the sum of the digits of this is going to be 36 for k equals 1, 2, all the way to 10,000. 10,000. Yeah, 10,000. And so you can see this if you So we can note 9,999 is really 10,000 minus 1. So whenever we add 9,999, we're adding 10,000 minus 1. And when we add this to, say, 9,999, we subtract 1 from the first digit. We add 1 to the fifth digit, which would be 0 in front of here. We got 19998. And note as we continue to add and subtract, add 10,000, subtract 1. Each time we subtract 1, this unit digit will go down 1. This fifth digit will go up 1. And note that once this hits 0, this is at 9. And if we subtract 1 once more, this goes down to 9. This loses 1. And this goes up to 9. This loses 1. Adding 1 here when this is at 9, this goes down to 0. And another one gains 1, so they oppose each other. And this process will be such that the sum of these digits stays as 36 all the way up to k equals 10,000, at which point it'll be 9999 followed by 4 zeros, which is still 36. If we add our number one more time, then we get the sum will be 72, and then it breaks down. But 10,000 is a lot bigger than 2014, so this number does work for our requirements. And now we just need to show that this is in fact the minimum number that works. So we want s of p equals s of 1001 times p. So we're going to consider 4 or less digit numbers such that A, B, C, D, each being the digit of a number, potentially 0, times 1001. This is A, B, C, D, followed by 3 zeros plus A, B, C, D. Note if A equals 0, this will just become BCD, BCD, and the sum of that is clearly going to be greater than our initial sum. So three to one digit numbers will not work for this. So we're going to assume we have a 4-digit number here, so A is not 0. So note when we multiply by 1001, our last 3 digits are always going to be BCD. So note if A is less than 9, then this will be A or A plus 1 down here at our final digit. And note that we're adding A is non-zero, A plus D. At some point here, a digit is being increased by 1, potentially A. And so if A is not 9, we're going to find that this sum, the sum of the digits here, will be greater than our initial sum. And so we can conclude that A, in fact, has to equal 9. Also, we can know if B does not equal 9 or C does not equal 9, we encounter a similar issue where if one of them is less than 9, then they increase by at most 1. The digits after them will be left alone. You won't have to carry a 1. And so somewhere in these 3 digits will increase a digit without decreasing the future digits, and we'll find the sum is again going to be greater than our initial sum. And so we can conclude A, B, C must all equal 9. Yeah. And so 9 plus d, if that, we want that to be greater than or equal to 10. If it's not, these 3 digits will stay 999. We'll find our sum. Again, we have an issue that the sum increases. So 9 plus d must be greater than or equal to 9. But note, because the sum of p equals the sum of 9p, and the sum is congruent to the integer itself, mod 9. So p must be congruent to 0, mod 9, because sum of p equals sum of 9p. And so this ABCD must actually be divisible by 9. So note 9 plus d must be divisible by 9. So d must be divisible by 9. So d is 0 or 9. But we can't have d be 0 because then it would be less than 10. So d must equal 9. And so we're just left with ABCD equals 9999, which we know works, and now we know is the minimum possible number. Thanks for watching. Please check out centermath.org, check out our blog, and follow us on Facebook and Twitter. Thank you.